This is great, the simplest train you can make. A battery and two high-powered magnets either end, going through a pure copper coil. The magnets have their south poles facing outwards. This is actually a version of a homopolar motor, and it works using the interaction between electric current and a magnetic field. So here's a battery, its two magnets, and some lines that represent the magnetic field between the north and south poles. When the magnets both touch the copper coil, a current runs from the positive of the battery through the copper coil and back to the negative of the battery. This creates another magnetic field inside the coil. Okay, there's this thing called the right-hand grip rule. It says that if the current is going round in the direction of your fingers, your thumb will be pointing towards the north. I can check that using a small compass and putting a current through the coil. So on the battery we've got a magnetic field that's going south-north, north-south, and when the battery puts current through the coil, it's creating a field that's going south-north, and that's pushing and pulling the battery train through the coil. But that can't be right. The north and south would attract each other, and the south and south would repel, so the battery should just sit there going nowhere. Well, it turns out the train isn't being pulled or pushed, it's being squeezed. If we look at the different field lines, you can see them getting further apart at the ends. And if we move our small compass around the magnet, you can see the slow change between north and south poles. The result of this is the predominant force is the repulsion between north and north and south and south. Imagine it a bit like squeezing a tube of toothpaste. Yuck. Let's try changing the polarity of the magnets. Now we've got the north poles facing outwards. So what's going to happen? That does not want to go in, but it will run in the opposite direction. If you've worked out why that happens, I'd love to read it in the comments. I'll put the magnets back the way they were. So what happens if we take a magnet off each end? So if the combined magnetic field goes down, the force goes down too, and the train runs slower. Let's make up another coil. Moves at a good speed. And now we'll stretch out the coil. And it moves slower. So what's going on? It looks like we've increased the length of the coil by stretching it out, but the length of wire that's actually in contact with the magnet has gone down. So if the length L reduces, then the resultant force F will go down too. So that just leaves the current I. And no great surprise if we use a battery that's got less juice in it, by juice I mean current. Less current available means less force. I'll make another coil, the hard way this time. One of these coils will make the train run a lot faster than the other one. Well, with the larger coil, there is a greater length of wire surrounding the magnets, but at the top and the sides of the coil, the wire is further away, so the resultant magnetic field, B, has gone down, and that overall reduces F, so the train goes slower. So now we know how to make a faster train.